Okay, so and I'm gonna share the screen. Okay, welcome everybody, and this is the continuation of our workshop on basics of T-ray metrology and time domain spectroscopy with advanced applications. So today, let us continue from the last time, and this is the user manual, as we talked about it a little bit last time. And today, I don't know if you have any question or thoughts on the user manual as we did last time.
What, on the first page or the table of contents, it mentioned error, 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 error. What was the purpose? What was the reason?
Well, what happened as you have the PDF, and from the Word file, the bookmarks are not correct. So when it's converted to PDF, it didn't find the right bookmark, so it gave errors. That's, that need to be fixed. That can be easily fixed. We'll do that at a later time.
Thank you.
Okay. So today, then we're gonna we have this, we have introduced the instrument, then imaging details, and today we're gonna the same instrument as you do the imaging. You can also do what they call is an electrical characterization, and a lot of times, electrical characterizations are important. Let's say a wafer maker, people who are making only the wafer and supplying it to the fab industry. As you know, silicon is a semiconductor. When they make the wafer, it is by itself is not conducting. So then they have to dope all the wafers for making it conducting, either P-type or N-type. There are two types of wafers. Both types are made by doping. And when you dope, then the carrier concentration is important. It has to be uniform all over the wafer. It also has to be within the specified value, etc. So how do we use T-ray technique to do that? So one of the thing is done. Yeah, friend has a question.
I have a very naive question. That is, when we are supposed to make the wafer conductive, so why do we use semiconductor to make the wafer? Why aren't we using any conductive material to make the wafer itself?
Good question. Good question. Absolutely. Yeah, we cannot make any metal to make a wafer, although some wafer has metal coating on it. The term semiconductor, as you know, this silicon is a semiconductor. So meaning that we can make it conducting or we can make it insulating. And that is the basis of PN junction, from PN junction to transistor, logic circuits, all of those as built on a wafer, it requires semiconductor. What happens, so let's say I have, it's a layer by layer process, and there are hundreds of layers on a wafer before it becomes a circuit, IC, or integrated circuit. So very complex process. It's a miracle by itself that this thing works the way it works. Maybe I should bring another. I have a lecture on that actually, in particularly introduction to semiconductors. So next time maybe I'll discuss that with you.
Yeah.
and this time, let's go through the instrument and the imaging, right? So once that is done, yeah, we did not introduce the semiconductor physics or chemistry or, the band gap engineering. It's an ocean by itself. And we are nibbling a few pebbles or not even that. So our goal here with this instrument is to solve as many problems as we can about the semiconductors. One of the problems we are talking here today is the electrical characterization, meaning that the manufacturer has made a wafer, or even they needed the manufacturers of wafers. How do they know, like Miles asked a few little while ago, that how do they know how much carrier concentration is in there? What is this is important. This information a wafer manufacturer must provide to the fabs, fab meanings where all the integrated circuits are made, foundry. They must have that information from the wafer manufacturer. So how do they measure the carrier concentration as they dope it with either p-type or n-type to make it p-type or n-type? So one way, there are 2-3 different ways. One is what they call the eddy current technique, which is mostly used when they put the wafer in the eddy current probe that measures the eddy current and computes the resistivity, which is what they want. So the mapping then requires moving the wafer here and there and get the position and the reading, local reading information, so that they can create a map. So the same thing here we have done with the T-ray. This is the whole wafer that is mounted on the stage, and stage are moved, and some 99 point or so measurement is done on the entire wafer. It could be less, it could be more, depending on the necessity. And user can define here that, okay, we're going to make a 99-point measurement. And then, the program takes care of that. Once that is done, then that goes in the data file. And then we bring here the model. How do we now convert the intensity numbers into the electrical resistivity? So, a fortuitous thing is that as the resistivity or conductivity, they are reciprocal to each other. As the resistivity changes of a material, its reflectivity also changes. So if we measure the reflected intensity of different known conductance or resistivity material, then we can use that data to model. So this is exactly that we have done here. As you can see, there are 4 samples. One is a silicon whose conductivity is known. I'm intermixing the terms conductivity and resistivity, but these are known. Then we had a graphene sample whose resistivity also known. Then we had a silicon germanium solid solution whose conductivity was known, as well as we had a germanium sample also known. So now if we measure all 4 of them, then we, based on their level of conductance, the reflected intensity is different. So we take this 4 number, average of this, and this, and this. If we plot that, then this is the plot looks like. So now we have a plot where resistivity versus intensity, reflected intensity. And then what we want to know is that based on, what is the reflectance and what is the resistivity. So we turn around the plot and we can come up with a model. So, I mean, this model can be other equal. So we have a way of modeling, and you can get into that at a later time. But once we have experimental data with certain relation between each and every data point, then we can come up with a best fit equation. With that, then we can measure the reflectance and calculate the resistivity. So advantage is that once you do that, once the model is ready, then from that point on, it's a matter of just putting in the machine and get the number instantaneously. It doesn't take any time. And then we can do that 99-point measurement and then map the resistivity of the entire wafer. And this has to be within certain limit before they can go on manufacturing all the circuits. And if the local variation is very high, then that wafer will not be suitable for circuit fabrication. So our model shows that these are the, here is the resistivity measured by eddy current technique. And here is the resistivity from our model. And then we're showing the percent disagreement is, within the experimental error limit. In fact, the T-ray is expected to produce better precision than the eddy current technique. So anyway, but there is, they are within the same ballpark, except there is some disagreement, which is normal. Any two technique is not going to give exactly same measurement. So now, as you can see, with the same machine as we did the imaging, we can also use the same scanner and map the entire wafer's resistivity, which is an important factor that the manufacturers need to know. This is a different picture of the same thing. So this is actually a 200 millimeter wafer, and the other one was 100 millimeter wafer. That's the difference.
Only on the surface or throughout the whole material?
You can do both. So what I have not shown here is that the process starts from the surface of the wafer. So then surface characterization, surface conductivity characterization or resistivity, this is called the sheet resistance, meaning that resistance per square. So it's important. On the other hand, think of another situation where we have a substrate of known resistivity on which we have another layer, they call epitaxial layer, or some other layer of different resistivity. So then an advantage of the T-ray is that not only we can measure the substrate, we can also measure both layers, measure the surface, then go deeper and measure the substrate. The other thing, another important thing happens here, we have data elsewhere, I don't have it here, not in this user manual. What happens is as you go deeper, let's say you have an epitaxial layer of few micron thick, then obviously substrate has very high conductivity, meaning that very low resistivity, and epitaxial layer has a lower conductivity, meaning higher resistivity compared to the substrate. Typical numbers may be, it depends on what they want to do on their design, but for example, you see here, silicon, this is an N-type silicon that has a resistivity or sheet resistance of 0.005 per square, right? Compared to that, if I had an epitaxial layer on top of that wafer, that could be, the resistivity could be, 100 times or 1,000 times bigger. So T-ray then can be used to measure both on the surface of the epitaxial layer as well as go through the epitaxial layer and measure the substrate. Now, what happens is, as you go closer to the substrate, there is a transition from the epitaxial layer to the substrate, to the wafer. This transition is a tricky thing to measure, really tricky thing to measure. I mean, there are techniques to measure them, but T-ray can very easily probe that transition as well. And that data is not here. We're not showing it here, but so you know. Any other point before I move to the other topic? Okay. The other thing is measurement of kinetics. And this kinetics is, kinetics is a generic name. Any property when tracked as a function of time is kinetics. What I'm showing here is just it's experimental arrangement. This one, so this is the box for the T-ray source and detector, etc. But as you can see, I have a beaker full of something, water probably, and then T-ray is going through the beaker into the, here is a detector here. So imagine that energy is coming from this box, Tn3di, getting through that beaker full of solvent into the detector. So now, if I allow some solute inside that solvent and with stirring, it will go into solution. How fast is going into solution? And what is the concentration of that solution? These are the two questions that becomes important. For example, this in the liquid in this beaker is actually a simulated stomach fluid, meaning that it's 1% hydrochloric acid solution. That's simulated stomach fluid. And then there is a heater, is the red thing, there's cartridge over there that controls the heat of this, because stomach fluid is usually at what, 99 degrees C or something like that. 97 or 98 or so. So this is a precise heat control. There's a controller here, heater control. And it can control within 0.1 degree Celsius. So you can set it up for whatever temperature you want. For example, 98 degrees Celsius to simulate the stomach fluid. And there is a stirrer, well, there are two different kinds of stirrers are there. And this one is you see that stirrer that goes from top into the liquid. It's not there is a bottom stirrer, it's not used here. But you could either put a stirrer in there and start it, or you can put this fan in there and keeps moving it, starting it. There's a starting control here. What's the point? Point is, if I put now a tablet in this simulated stomach fluid, then I can measure how long does it take to dissolve. And that is important because the dose and all of those things depends on how fast it's dissolving. Is it a one-step or two-step process? Some tablets they have a coating, slow dissolving. All of those things can be characterized by this experiment. For example, here is a set of data. As you can see, we put the dissolution kinetics of ibuprofen tablet, 600 milligram in, actually it's in stomach fluid, not water. It could be, this data could be at water at room temperature, but there are other data which is, more precise man should ask you. So another experiment somewhere is there where it was in simulated stomach fluid. So this x-axis is the time axis. We can see how fast it is dissolving, and all this information then becomes kinetics, becomes important for the dosing and purposes. So, the details of the procedure is given here. And that's all for this particular user manual. So, you want to make any comment or question here?
Yeah.
Mm-hmm.
I didn't quite understand, like, how is the stomach fluid been stimulated?
Well, ideally, if you want to make the exact measurement, probably we should put a syringe in the stomach and bring some fluid out. But if you know the composition of the stomach fluid, then you can make a solution like that. So usually stomach fluid has a lot of other things, but usually it is 1% hydrochloric acid in the stomach and water. So, but there are, of course, enzymes and all of those things, bile secretion. I mean, we cannot do that, or we didn't do that. I don't know, more sophisticated experiments probably would be able to do that. But here, all we did is assume it's only 1% hydrochloric acid solution. So you take 99 milliliter water, 1 milliliter hydrochloric solution, or so on and so forth, and put it at a temperature which is closer to what is inside the stomach. And then assume that this is a simulated stomach fluid, right? That's what is done here. And then agitated or rotated by this mixer. The point here is that we want to see, think about this tablet. If we raise the temperature, it would be dissolving faster. And then we can measure that here. If it was a different tablet, solubility of tablets should be different, then this curve will tell us how fast, in this case, you see the complete dissolution took about 2,500 seconds or something like that. So it can be faster, it can be slower, but we can quantify that from this measurement. That's the whole point. There are sophisticated experiments can be designed, but this is just a simple way of showing that, kinetics can be tracked down. Good question. Any other point? All right. So now, given that, let's now introduce the silicon carbide today, and then we'll go from there later. Silicon carbide. Here we go. Silicon carbide crystal growth issue. So silicon carbide has a very nice history. And initially, this gentleman in the 1800s, name is Edward Acheson, Acheson. So he accidentally discovered this material, what he then called is carborundum, because he heated the carbon and silicon crystal, some kind of silicon crystal, and found a bluish material. And he thought he was going to make artificial diamond by that way. And then it became this, he called it carborundum. Then the process was perfected a little bit, used to call it moissanite. And eventually when we produce it in the factory with silicon and carbon, it's a silicon carbide. Why it is important? Because 99.9% of all electronics is based on silicon, not silicon carbide or anything else, gallium nitride or anything else. But silicon has a tendency of lowering the operating voltage and temperature, stable room temperature. So as you know, in the old days, they used to make CPU running on 5 voltage, 5 volts, then it's 3 volt, and so on and so forth, going down. Because silicon is more stable at low power. Higher power may increase the temperature, which then reduces the performance. But then there are situations where we need high voltage and high temperature operation. And that's where silicon carbide comes in. Silicon carbide is a wide bandgap semiconductor. That's why it can tolerate higher voltage and higher temperature. So, but growing the silicon carbide is a big challenge. Even today, as I showed at the very beginning, I don't know if you remember, but silicon boule or ingot can be single crystal in silicon ingot can be grown 2 meter, 3 meter long. But for silicon carbide, even today, we cannot grow longer boule. It's 500, if we can, not even 500 millimeter, it's more like 40, 50, 60 millimeter. So silicon carbide is very hard, so it doesn't need to be as thick as per wafer. The thickness can be thinner than silicon itself. But still its growth and production is low. So question is, can they produce longer boule like silicon? Not yet. And the question is why. We try to understand that. The process that they use today mostly is called physical vapor transport, also known as seeded sublimation deposition. And we are trying to use the T-ray to probe that and find what happens. Main issues are silicon carbide crystal is grown at high temperature. So when silicon itself is grown about 1400 degrees Celsius or so, silicon carbide is much higher, 2200 degrees Celsius, or even sometimes it can go to 3000 degrees Celsius. Way more higher temperature than silicon itself. And because of that, as I will show here, this is the physical vapor transport process. I have borrowed these pictures from somewhere. I should have a reference here. I forgot that. It's probably, anyway. But as you can see, they take the silicon carbide source, which is a powder carbon and powder silicon, and they sublime them, and there is a seed crystal over here, and then the silicon and carbide goes and forms a single crystal on that seed crystal. But in that process, and the heaters are these darts are the as they call is the induction heater outside that crucible. So because of this region, as you can imagine, the heaters are here, heat coils are here, then there is going to be some kind of a gradient inside the chamber where the crystal is growing. And in fact, there is a radial gradient and there is also an axial gradient. All of those things are making it, there's a mistake here, it's 2200 degrees Celsius, not Fahrenheit. Okay, so because of that gradient of temperature gradient, they are now trying to find a way of minimizing that gradient, but nonetheless, still there are other issues because this crucible at that high temperature, who knows, may be contributing some impurities in there. The feeding pipes or whatever the arrangements are, everything may contribute at that very high temperature. So eventually they get this ingot or boule and they slice them into, different number of wafers. This process is same for silicon and silicon carbide, except in silicon carbide, they are slicing by laser, which is much better than by other technique like blades and stuff like that. So what happens if we take those wafers and image them, and this is an actual wafer, scanned on a simple scanner, in all the office scanner, remember those, flatbed scanners. So we put it on the scanner flatbed and get that image, but I'll show you optical image later. What happens when you do the imaging with T-ray, same exact wafer. Both of them are same exact wafer, side by side. This kind of thing that comes from inside is not due to roughness. There is no actual pattern on the surface of this particular wafer. This is blank. And yet, T-ray sees this kind of thing in there. So a big question is, where is this pattern coming from? And, up until today, we don't have any conclusive answer to that question. We don't know yet, but we're trying to find some clue. So if we compare those images with optical image, this one, this number A is the optical image of the same wafer whose T-ray image is next to it. This is the most modern machine that people have today on the left side image, the optical image. So this one is with epitaxial layer, this one is without epitaxial layer. And the other experiment we did is the same wafer. We had the X-ray investigation done. So as you can see, this crazy looking pattern inside that is revealed by T-ray is actually in there. Optics see that a little bit, not as clear as T-ray, but as you can see, because this is mirror image, so what is on the left side went to the right side and so on and so forth. But nonetheless, those things are there. So meaning that this crazy looking image that T-ray has revealed is not an artifact. It is actually there, the real thing. X-ray cannot see it, but optics see a little bit. T-ray see a lot better, a lot clear. So when we can see better, when we can see clearly, then the process people can take this information and try to make their process better. Because eventually it has to be like silicon, right? Let me show you. You see, if we put the same process we done on a silicon wafer on the left and a silicon carbide on the right, silicon wafer don't have that kind of crazy feature. There could be, more than one reason, but as of now, we really don't know what the reason is. But you see this image again, and then question is, if this boule is sliced into number of wafers, then is it only one wafer from the same batch? Same batch that see that pattern, or all of them? And in fact, all of them see the same kind of pattern. As you can see, it's the same thing going through the whole boule. So that means our first assumption that this crazy feature is actually within the boule. Okay, and when you slice that boule into different wafers, it shows in the wafer. So if it is actually within the ingot itself, this is the proof of that. So if it is in the ingot itself, then what can we do to fix the process so that this is not there? Because this kind of imperfection is not surface roughness, therefore it is the material issue. Okay, therefore they must fix it. And other thing is that this instrument can also measure, also do the imaging in both in reflection and in transmission. So what you see is black in reflection is white in transmission, and vice versa. But nonetheless, the pattern is still there. As you can see, what is in reflection, just in the opposite phase in transmission as well. So it is a material issue. That's what we believe. And as I showed, it's not in silicon, it's only in silicon carbide. So that means the T-ray image is providing some important clue so that the people who are involved with the process, they can learn from here. They can change variables and see how it works, and eventually they will fix it. That's the idea. So let us stop here today. Next week, so I'm not here, unfortunately. But you guys should work on your project. And week from next week, would you be interested to make a presentation on your project? Then you have 2 weeks to prepare on that.
Okay. Yeah.
Is that okay, Miles?
Yeah.
Okay. All right. And then I think we'll spend probably 2 or 3 on the spectroscopy, and that would be the end of it, right? Any questions so far or any comments so far, don't hesitate. You can even email those if you have, and I will try to respond. Whenever you have questions, just feel free to ask or email.
Thank you.
All right, so let us stop for today. And yeah, question.
Travel safe.
Oh, thank you.
All right.
Yes, it's very uncertain and unpredictable these days. I hope I come back in one piece. Thank you.
Have a good weekend.
Okay,
you.
you too.
Thank
Bye.
you. Thank you.